Hey everyone, welcome back to the channel and welcome to a new school year. In the spirit of new beginnings, here's a new look for the channel. We've got a new logo and a new sort of format for the title slide. So this is the setup I'll be using over the course of this year, where the title slides will look like this. And I'm going to try to keep things color-coded, where the text at the top and bottom are blue for math and green for science, which is a little different because last year we did purple for science and green for geography. But since I'm not your geography teacher this year, we're going to use blue for math and green for science. So hopefully, if you're going through videos on the channel page, you'll be able to tell at a glance whether it's a math lesson or a science lesson based on the color of the text. The title, of course, itself is white here, and that's what I'll keep doing just because I think it looks better than blue and green when I was sort of playing around with it. But yeah, hopefully you'll still be able to tell just by looking at the thumbnail of the video whether it's a math lesson or a science lesson, but I will again be organizing the videos into different playlists so that hopefully you don't get lost looking for the next lesson that you're supposed to watch. But yeah, so we've got lots of different and exciting topics to look at this year, so let's dive right in. So my original plan for this year was to post roughly one video per week, and I say roughly in the sense that there might be some videos where either the topic is really complicated and I want to split the lesson into 2 or 3 parts, where the 2 or 3 parts would all be smaller than if it was just one big long video. There might be some weeks where there are no videos posted, and that will sometimes be designed to help you guys in the sense that maybe if I've assigned a science test one week and a math test the next week, then maybe you won't have a lesson for one of those classes in the week in between, just while you're busy studying and writing your tests. So things like that. And there might be the occasional week during the year where I'm not able to post any videos due to being in school myself and having my own exams to write. So there might be some weeks that have a few more videos and some weeks that don't have any videos. In general, I'm going to try to post about one video a week. It'll probably be too long for you guys to finish in one class. I've just looked at your schedule this morning before I started recording this one, and it looks like the schedule's got 4 slots in the week for math lessons and then one for science lessons. So for the science lessons, I'll really try and keep it so that you can finish the video within one lesson. For math, I'm not going to be quite so bothered about how long the lesson is and whether you can finish it in one class or not, because if you can't finish it, let's say on a Monday, then you could continue on the Tuesday and finish that lesson then. I'm also going to see about giving you guys homework that you could work on in the remaining classes for the week. So for example, the schedule the last time I saw it was that you guys have 4 math classes with me each week. And so the way I kind of envision it would be a couple of classes where you're going through a lesson or two. Maybe if I post 2 videos, then you can spend 3 classes going through that. And one day that's purely just working on an assignment or studying for a test or things like that. Of course, that's something that still needs to be worked out. Please bear with me as I try to figure out sort of the optimal way to go about things, because my class has just started as well, so I've got a lot of things, scheduling things to figure out. I should be able to make it all work. I just kind of need to find the time to make sure that I'm able to do things on a regular schedule. But anyway, I will give you guys further updates when I know more about what the plan is going to be. All the videos are going to be posted on this YouTube channel where you're watching this right now. This is the Esperanza Online YouTube channel. And if you have Instagram, you can follow the Esperanza Online Instagram account as well. And I've actually just created a website this morning as well where I can post updates and sort of post the videos that you need to watch each week in case I happen to be ahead of schedule with posting the lessons, just as a way for you guys to stay organized and give you and your parents a way to get in touch with me if you have any questions or concerns. I'll probably make a short video after the introductory lessons for each class, explaining, sort of just navigating through the website a little bit, so you guys can have a look at that. With regards to assignments and tests, at the moment, I don't know quite how that's going to work. Perhaps we'll sort out something with a Google Classroom, or I'll have you email your work to me and I can mark it, or perhaps hand it in to another teacher who can either mark it themselves or send it my way. So I'll sort those things out, and once again I will give you guys further updates when I have more information about that. For the time being, the priority is just to get you guys started with a few lessons, and then we'll figure out assignments and tests as we go along. Now, keep in mind that if you ever need to rewatch a lesson, the big advantage to having these lessons being on the computer and on YouTube is that you can go back and watch them again. This is something that has helped me a lot in the time that I've been taking my classes online. It has been to be able to pause and think about, what did the teacher just say? What did the professor just say? Go back, rewatch it, pause to write down my notes so that I don't have to, listen to the professor speak and write my notes at the same time. So try to make use of that if you can. Now, as I understand it, you guys are back in the classroom in person this year, so you shouldn't have to worry too much about sort of keeping track of your own schedules and making sure you stay caught up, because it sounds like that's going to kind of be done for you because you're watching the videos in school. But if you ever need to rewatch a lesson, just look up the Esperanza online channel on YouTube, and you should be able to find it fairly easily. If you want to subscribe and hit that notification bell so that you guys can see when new lessons come out, that is totally up to you. It's the easiest way, I think, if you want to get ahead of schedule. If you want to watch the lessons ahead of time, then if you subscribe to the channel, you'll see when I upload a lesson, which will probably not be during your school day. It'll probably be on weekends or perhaps in the evenings. So if you ever want to watch them ahead of time, please feel free to do that. And a word of advice, for some of the topics, maybe not right at the beginning, because we'll always start out kind of slow and simple. But for some of the topics, especially later on in the year, they can be kind of confusing. So it might be in your best interests to try and study some of those topics multiple times. So what I mean is, watch the videos in class, take some notes, watch the videos again, maybe that night or maybe that weekend or something like that, just to revisit the idea, go through your notes, make sure you understand them. Ask questions to your classmates, and ask me questions. You guys should have my email address. If not, I will make sure that you guys get that one way or another. And if you have any questions, or something's not making sense in one of the classes, or you're not sure about, hey, do I need to watch this video for the test? You can send me those questions either directly through email, or I set up that website so that you guys can get in touch with me in different ways, and that your parents can get in touch with me that way as well. So hopefully there are enough tools kind of at your disposal so that you can go through the videos go through the topics that we study in the videos, and that you have enough time and resources available to do the homework and to get in touch with me if you have any questions. So if you have any questions about any of that, get in touch with me in any way possible, whether that's leaving a comment on the video or an email or through the website. All of those options are there. The link to the website is going to be in the description of the video, so you should be able to find it there. But yeah, so that's sort of all the housekeeping items, I believe. So if I'm not forgetting anything, let's continue. Okay, great. So now we can look at this math class in particular, and we'll have a look at the topics that we're going to study. So we're going to open with a little bit of a basic review, we'll talk about the metric system, which is a really important system of measurements. We'll talk about some differences between the imperial system and the metric system, just because that tends to be a really confusing point when we try to apply math to things in reality. This can be a big point of confusion. So we'll start by reviewing the metric system. What is it? Why is it so great? Why do most countries use it? We'll take a look at scientific notation, just because it makes it easier to write big numbers and small numbers in a really condensed sort of way. So we'll take a look at that before we jump into a big main unit. So our first main unit is going to be geometry, where we'll look at the properties of simple shapes. So by simple shapes, I mean things like squares and triangles and parallelograms and things like that. And we'll look at their properties. So, what's the easiest way to figure out the perimeter of a square? Or what makes a square a square? What makes a rhombus a rhombus? Things like that. So we'll look at the absolute basics of these are the simple shapes that you'll be encountering reasonably frequently, and here are some properties about those shapes. And then we'll jump into perimeter and area after that. And where I've written 2D shapes, that means so all things like squares, rectangles, parallelograms, things like that, circles. And then after that, we'll take it to the next level, and we'll talk about the 3D version of perimeter and the 3D version of area. So if you think about a shape, like, well, bear with me while I draw, a square. So if you've got a square or square-ish type shape, so the perimeter is the total distance going around the outside of the shape. So if you were to build a fence around this square area, if it was like a square field somewhere in the city, and if you wanted to build a fence around it, then the length of the fence that you would need is the perimeter of the square. Whereas the area of the square is how much space you have inside. So if you wanted to plant seeds or sod to grow some kind of plant, or to put fresh grass everywhere, and you needed to know how much grass do you need to cover the entire inside of the square, that's where area comes into play. So that's the 2D version. The 3D version is surface area and volume. So once we look at shapes like squares and circles, we'll then extend it into 3 dimensions, where we're dealing with things like cubes and spheres and things like that. So in the case of a cube, it's not the best cube I've ever drawn, but just bear with me. So when we're talking about surface area, that's like if you had a cube and you wanted to paint the outside of it, then that's basically the area of all the faces of the cube that you can see, is the surface area of the cube. And the volume is how much space there is inside the cube. So if you wanted to fill the cube with water, how much water could you put in the cube? That's volume. So there are some differences between perimeter and area, surface area and volume, and we'll talk about those when we get to that topic in the class. After we go through our geometry unit, we'll continue on with algebra, and that's where we'll focus on understanding the use of variables and why variables are useful and how we use them and how we can figure out what value a variable represents and things like that. So if you've ever seen, an equation that looks like maybe like, I don't know, y equals 3x plus 2 or something like that. Most of you should have seen what this means last year when we studied, or maybe not last year, but the year before that when we studied linear functions. But whatever. Basically, when you see mathematical equations with letters in them, that's got something to do with algebra, and we're going to explore what those letters mean and what we can do with them and why they're useful and why they start showing up in math all the time after when you get to like a high school level, when you start studying calculus and then go into university, all the math becomes letters and no numbers. So we'll explore why that's the case, why it's important, and then we'll explore how to solve some problems, some simple problems involving just one variable or two or more variables. Um, and we'll talk about that more when we get to that part of the class. After that, we dive into the good stuff. This is the stuff that tends to be studied around the age of 14 to maybe 16, 14 to 15-ish maybe, here where I am. So we'll begin this sort of heavier part of the course with linear functions. So that's a fancy way of saying lines. Most of you should have seen the Cartesian plane before, which is basically just that big plus sign in the middle of a grid, and you can use that to plot a bunch of lines and curves and stuff like that. So if you've ever seen something like this, if you've ever seen like a mathematical function that's on this grid with a big plus sign in the middle of it, that's making use of the Cartesian plane. And so we'll look at the Cartesian plane, what it is and how we use it, and then we'll look at how to draw lines in a mathematical way on these grids. Then we'll basically do the same thing, but for quadratic functions. Now, what on earth is a quadratic function? So a line on a graph might look something like this. But a quadratic function it takes the shape of what we call a parabola, right there. And it looks something like this. Something like that. And you can have a parabola that sort of opens up the other way, like an upside down version of that green one, something that looks like that. And these shapes, these parabolas, they're pretty important if you want to describe things going on in the world, because if you wanted to throw a ball, well, if you throw a ball and you wanted to know where it's going to land or how long it's going to take and things like that, when you throw the ball, the trajectory that it takes before hitting the ground is basically a parabola. So these things tend to be really useful if you want to explain how things move. Like if you throw an object, or even if you fire a bullet from a gun, they also follow this kind of trajectory, even though they might not immediately look like it. So these things actually show up a lot in nature, but of course that'll be something that we explore more in science. In math, we're going to look at the numbers side of parabolas. So not so much how they're used or where exactly they show up, but we'll talk about how to construct them on a graph. And so the idea for me planning these two classes is that I teach you how to use the mathematical tools at your disposal in this class, and then in our science class we'll explore why those tools are useful and how we can use them to explain things that we see in nature. And then the last area of the course that we'll study this year is trigonometry. So this basically starts off with studying a lot of different weird properties of triangles. They're not really weird properties, they're just things that you don't really think about until you start studying trigonometry. Before that, they're just triangles and there's not much more to them. But we'll explore some different concepts in trigonometry. You guys might have heard these words here, sine, cosine, and tangent, and those come up quite a lot in trigonometry. And then you guys might not have heard these three words before, but they're not as scary as they sound. And we'll look at some uses of trigonometry. So if you have a triangle that looks something like this, something like that, and if you know how long this side of the triangle is, and you know how long this side of the triangle is, you can use trigonometry to actually figure out how long this side is. And you don't necessarily need this angle to be 90 degrees, because then, you can use Pythagorean theorem and things like that. That's the a squared plus b squared equals c squared. You guys have probably seen this before. If not, don't panic. Don't worry about it. We will get to all of these things in due course. But you could use this to figure out a side length if you know the other two side lengths of a triangle, but it requires that you have a 90-degree angle. Some of these other things in trigonometry, namely sine law and cosine law, don't require this 90-degree angle right here. So you could have a triangle that looks like this, where none of those angles are 90 degrees, and you could still figure out the side lengths and the angle values if you're given a little bit of information about the triangle. So those are the kinds of concepts that we'll study in this course. Now for me, one big problem that I've sort of had with math when I was in school is, honestly, if I didn't have this problem with math, I might have gone into math in university. Like, I might have been a math student. Instead of that, I'm a physics and astronomy student. But so my big problem in math, for me personally, you guys don't have to have the same problem at all. For me, it was that I didn't like, especially towards the end of high school, that I would put in so much work to go through the problem, and then the final answer didn't necessarily mean anything some of the time. Of course, there are questions where you do need to use math to come up with an answer, and the answer actually means something in the context of the question. But there are other questions where you go through all this work and you end up plotting a dot on a graph, and you're saying, yep, that's the answer. And what bothered me was that there were questions where that dot on a graph didn't really mean anything. It didn't really stand for anything. And a lot of people, I think, have a similar problem to that, where they don't understand why they have to put in the effort to learn something that they don't like or don't understand, and it seems like they're never ever going to use it. And so I'd like to take a little bit of time just to show you maybe a few uses of it, and then a couple of examples of how amazing a tool it seems to be for us when we're trying to learn things about the world we live in. So one of the things that makes math so useful is that mathematical patterns show up all the time in nature. If you have questions about something that happens in nature, chances are, if you dig deeper and deeper and deeper, you'll find math somewhere in the answer. We'll talk a little bit more about this later on, and if you guys have any questions for specific examples that maybe you can think of, and hey, I don't really see how math comes into this, then let me know. We could talk about it. Math, for me, it seems like it's a really, really powerful tool that lets us learn things about the world or about the universe that we would not have been able to do without it. So, for example, and the example that I'm going to talk about is figuring out the size of the Earth. Just because of how big it is, it's really hard to figure that out. You can't dig down to the center, it gets too hot, and you can't really measure, with a ruler on the ground and then just kind of turn it end over end until you go around the whole planet. You run into problems with oceans, and you probably just won't be able to do it because it's such a long distance to cover. That we can use math to figure things out in more convenient ways than by having to, for example, dig down to the center of the Earth or through the Earth to figure out how big the planet is. So things like that. And on top of math just appearing to be useful because it shows up in nature, it is important for a lot of professions. So depending on the kind of work you want to do, when you start your careers, for a lot of jobs, it's useful, maybe not a requirement, but definitely useful to be good at least basic math. But also for things like managing money, understanding things like tax and interest and all of that stuff. If you're doing construction work in your house and you need to buy a certain amount of a material, or you need to cut a certain length of wood or something like that, uh, these the tools that you learn in a class like this one can really go a long way in helping you understand the concepts that you need to when you're doing stuff like that. Um, if you're planning a trip, if you're converting between units like Celsius and Fahrenheit or dollars to pesos, cooking, we've got fractions showing up all the time in recipes. There are these sort of basic ideas in math that are really important to understand how they work, like is 1/3 bigger than 1/4, or is 1/4 bigger than 1/3, things like that. Um, so those real basics are really important to understand. And then some of the things that we're going to study here, like things like quadratics and trigonometry, they might not show up as frequently as things like geometry, but they are still useful, and especially if you're going into certain professions that require a decent understanding of math and using numbers and manipulating numbers. It can be really important to you to know these things so that you have those options available to you when you are trying to decide what you want to do with your life. So now let's jump into a look at mathematics in nature, just as an example of how mathematical patterns show up all around us. So some of you may have heard of the Fibonacci sequence. And so this is basically a list of numbers where each new number in the list is the sum of the previous two numbers in the list. So I personally like to start it with a 0 and a 1. Some people say it just begins with like the beginning of the Fibonacci sequence is just a 1 and then another 1. But I'm going to go with starting with a 0 and a 1. So if you start with a 0 and a 1, like these two right here, that's the beginning of the Fibonacci sequence, and we just kind of decide this is where it starts. And then from those two numbers, you can generate the rest of the Fibonacci sequence. So what we've got up here is that each new number in the list is the sum of the previous two numbers. So the sum means you have to add the previous two numbers together to get the new number. So if we look down here, 0 plus 1 is 1. So that's this new number right here. And then we want to get the next number, so we add up these two. 1 plus 1 is 2. And then if we want to get the next one, 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8, 5 plus 8 is 13, and so on. And you can generate this list of numbers that doesn't seem to really mean anything aside from just being a cool thing you can do with numbers. That, hey, look, I can generate this list of numbers using this sort of pattern where each new number is the sum of the previous two numbers. But it doesn't seem like it has any sort of applications in nature or anything like that. If any of you are interested, this is how you could write the Fibonacci sequence mathematically, and this is an example of how you can use a bunch of letters to condense down this list. So you don't have to write down the entire Fibonacci sequence, which is good because it doesn't end, and you can just sort of write it this way, and this technically contains all of the numbers of the Fibonacci sequence inside of it. But anyway, so we've got this seemingly meaningless sequence of numbers, but then we find that the Fibonacci sequence appears in nature, in that a lot of there are a lot of quantities that we can measure. So for example, the number of petals present on a flower, or the arrangement of the spirals of a pine cone, things like that. The number that you find, if you count up the number of petals for a lot of different things in nature, those numbers tend to be numbers in the Fibonacci sequence. And I haven't studied the Fibonacci sequence enough to know if people have found a reason as to why, but it does definitely seem interesting that we've at least found that this seemingly meaningless mathematical construct actually appears in nature. And so like you can look at this for as an example. Let's take this flower up here. If we count the petals starting here, that's 1, 2, 3, 4, 5. And then over here we've got 1, 2, 3, 4, 5, 6, 7, 8, I think. I don't know if there's a last one in there, but if it's 5 here and 8 over here, then that's exactly my point. We've got 5 plus 8 is 13, and I can't go back a slide when I'm recording, um, but 13 is a number in the Fibonacci sequence. And of course, there might be flowers here. I haven't gone through and counted the petals on each. You might say, oh, you know, there are a bunch of flowers here that don't have the right number of petals. This is it's possibly the case that some of these flowers don't have the same number of petals, but it does happen a lot in nature that we see things that have these specific numbers. And you can read about that more if you're interested. But this is just sort of just as an example to sort of get you started. There's another mathematical concept that appears in nature called fractals, and these are shapes that these are patterns where basically if you have a shape that repeats the pattern as you zoom in or as you zoom out. So it would be like, for example, let me see if I can draw like a simple one. So like so I guess for example, so suppose you've got like if you've got a shape that's sort of got this kind of pattern to it on the sides, you know, and you know we could just say this kind of continues on for you know, you're zooming into this edge of the shape and you see this pattern on the edges, and then suppose you zoom into this area right here, and as you zoom in, if I can zoom into, if I sort of draw the zoomed in version over here, that you thought it looked like this. But when you zoom in, you can see that there's actually more of the same pattern in here. And so the pattern itself repeats. And then maybe you could zoom in again and you see that there's even more of those little sort of the jagged square things when you zoom in, or you zoom out and you find that this whole shape here is actually just one of these on a larger version of the same thing. It's kind of hard to explain, but an example here in the picture is in the leaves of ferns. So if you look at a fern, the leaves of the fern follow the same shape, the same kind of pattern to how they look as the whole fern itself. And so that's an example of basically if you zoom in to a shape that's got this fractal nature to it, it looks the same as the original when you zoom in or when you zoom out. And it's a really neat concept in math, and we can see as an example with ferns and also with like branches and leaves and things like that, this concept from math appears in nature as well. And another really interesting one is music and its relationship to mathematics. So the pitch of a sound, so how high it sounds or how low it sounds, depends on the frequency of the sound wave. Now, don't worry about the technical terms there. It's all sort of down to the physics of waves and all that stuff. But basically, high-pitched sounds have a really high frequency. So if you were to draw out the wave, a high-frequency wave has the crests and troughs, the ups and downs, really, really close together. Whereas a low-frequency wave has them spread apart, so like that. So a high-frequency wave, if it's a sound wave, it generates a high-pitched sound, and a low-pitched sound has a low frequency. So a low-pitched sound would have a sound wave that looks more like this, and a high-pitched sound would have a sound wave that looks more like that. And pitches that sound nice together, so if you hit two keys on a piano, for instance, Pitches that sound nice together follow nice mathematical patterns. There are ratios between the frequency of one note and the frequency of another note. And if you can if the ratio can be reduced down to a nice number, then those pitches sound nice. And if you can't really reduce it down, then it doesn't sound nice. And as another example, if you play the same note but in a different octave, so you could have in a do re mi kind of scale, you have the do, and then you've got the do that's up at the top, the high end of that scale, and then there's another do above that. And if you're using the names of the musical notes, then that would be like C, middle C, and then a higher C, and then a higher C. And so as an example, the note A, which is just below middle C on a piano, so there's C and there's B and then there's A. The A key on a piano generates a sound with a frequency of 220 hertz. And if you go exactly one octave up, so if you hit the A key at one octave up from there, then it's got a frequency that's exactly double. And if you go to the A key above that, it's double of that. So there are these patterns in music that we'll call this note an A and we'll call this note an A because they sound the same, but one's an octave up. And we find that the frequency of the sound waves that they generate when you listen to them are multiples of one another. They're doubles of one another. So this one is double that, which is double that. And so you can guess that the A key that's an octave below this one will have a frequency of 110, because that just makes sense with the pattern. And so this is the kind of way in which math appears in music. There are other ways as well, but this is just an example to sort of whet your appetite. So now I want to go through an example of the power of math. This is the example I was mentioning briefly before, where we can use math as a tool to help us learn things about the world or about the universe that we would not have been able to study by ourselves otherwise. And so one example of this is calculating the circumference of the Earth. So way back in the 3rd century BC, there was this guy in Egypt named Eratosthenes, and he calculated the circumference of the Earth using mathematics. And so he lived in the city of Alexandria. Maybe I should have put a map of Egypt in here, but bear with me. So he lived in Alexandria, which is way up in northern Egypt, if I'm remembering correctly. And he learned through some reading he was doing that in the city of Syene, further south in Egypt, vertical objects, so like if you had like a stick that you planted in the ground, or if we think about more modern day, if you have like a telephone pole or things like that. Of course, there were probably no telephone poles or similar structured objects, but if you had like a pillar for a temple or something, that was outside where the sunlight could reach it, then at noon on the summer solstice, those objects, like those pillars and stuff, would cast no shadows whatsoever. And what that meant was that the sun was directly overhead at that time. And so you'd be able to see it as well if you had like a well. So if you've got like a well like this, and then it goes down into the ground, and you've got people out here. So if the sun was anywhere besides directly overhead, so if the sun is like over here, then the rays from the sun will come in like this, right? And so the sunlight will hit the walls of the well in here, but not go all the way down to the bottom. But when the sun is directly overhead, so like up here, then those rays are coming straight down. And so you'll see that the sunlight actually goes down and hits the bottom of the well instead of the sides of the well. And it's a similar idea that if you've got like a pillar, a vertical pillar, then if the sun is over here, then the rays come in like this, and it casts a shadow. It'll cast a shadow on the opposite side. But if the sun is not off to the side and is instead directly overhead, then there'll be no shadow whatsoever. And so this is something that people had noticed as something that occurs in the city of Syene. And Eratosthenes thought that this was kind of weird because this never happened in Alexandria, where he lived. Those objects, those same kinds of objects, vertical pillars and such, would still cast shadows even at noon on the summer solstice. And so he thought this was weird. The understanding at that time was that Earth was flat. So if the Earth was flat, then you would expect that a shadow in Syene would look pretty much the same as a shadow in Alexandria. So if there is a shadow, if you took like exactly the same object, if you had like a pillar that was 3 meters tall exactly in Syene, and you had the same pillar, another 3-meter tall pillar in Alexandria, you would expect the objects to cast shadows of the same length and in the same direction and all that stuff. If there's no shadow at a particular time in Syene, you would expect there to also be no shadow in Alexandria at that time. But what was found through Eratosthenes' observations in Alexandria and his readings about how things worked in Syene was that there would be no shadow in Syene, but there would be a shadow in Alexandria. And so this led Eratosthenes to the conclusion that the surface of Earth must be curved. So instead of thinking of Earth as flat like a disk, now you can arrive at the conclusion by this simple fact of shadows and how they work that the surface of Earth should be curved. And here's a diagram to kind of explain it. So on the left side here, this is the expectation versus reality. So on the left side, we've got expectation here. Alexandria is up here with this sort of obelisk type structure, and Syene is down here with another identical structure. So if the sun is, wherever it doesn't matter where the sun is, you can see that there's a teeny tiny shadow there. I think what's effectively trying to be shown here is no shadow, but you can see there's a teeny tiny shadow right there in Alexandria, and there's a teeny tiny shadow right there in Syene. This would be expected if the Earth's surface was flat, but this isn't what we actually see. So if you instead take that surface and you curve the surface of Earth, then instead you can have that there's no shadow, effectively no shadow. It's a really tiny shadow there, but we can treat that as no shadow down here in Syene, but a pretty pronounced shadow at the same time, at the exact same instant in Alexandria. And so this matches the observations of the shadows as seen by Eratosthenes and by the folks in Syene. And so from this you can conclude that Earth's surface should be curved. So if you've gone from a flat Earth that's a disk into a curved Earth that's a ball, the next sort of reasonable question is, well, okay, if it's a ball, how big is it? And so that was the question that Eratosthenes sought to answer. So what he did was he hired someone to pace the distance, to basically walk directly from Alexandria to Syene and keep track of how far he had gone. So it's really inefficient and difficult to do that, but it's still better than having to walk all the way around the planet. And at least there's no problem of an ocean between Alexandria and Syene or anything like that. So anyway, what he did was he asked a guy to walk from Alexandria to Syene and measure out that distance. And so what Eratosthenes did was, if you've got, so let's look at this diagram up here. So if you've got these yellow lines are coming as rays from the sun. The sun is far enough away that when those rays arrive at Earth, they're effectively all parallel to one another. So when you've got these rays coming in from the sun, like this, then suppose you've got this stick, this little black line there, you've got this stick planted in the ground in cyan, and you can see that the ray of sunlight is hitting that stick directly, so there's no shadow. But for the other stick, over here in Alexandria, the ray of sunlight is coming in at a little bit of an angle. So we have this tiny angle in here that we can measure. So we've got the stick in the ground, and we can see that the ray of light is not coming in directly on top of it. So we've got this tiny angle in here that we can measure, and we can measure the length of the shadow. It's kind of the same thing. It would give you the same kind of conclusion. And then using a little bit of math, you guys might remember this from previous math classes that you've taken, is that if you've got two parallel lines, so here we've got the parallel lines of the rays of the sunlight, and then if you pretend that the stick in Alexandria goes all the way down to the center of Earth, and the stick from Syene goes all the way down to the center of Earth, then the angle between those two sticks when they hit each other is the same as the angle up here between the stick and the ray of sunlight. If that's not something that you remember or understand, don't worry about it too much. I'm just trying to make a point of how Eratosthenes was actually using math, but it's okay if you're not following along perfectly right now. But anyway, the idea is Eratosthenes knew this property about angles, that if he can measure the angle here, then he knows the angle down here already. The thing he needed was the distance between Alexandria and Syene, so that he could turn the angles into lengths to figure out how big the whole planet is. So he made a measurement of the angle, and he found that it came out to be about 7 degrees-ish. And so what happened was, so he measured the shadows. He got the angle to be 7 degrees. And the guy who paced out the distance between Alexandria and Syene came out with a specific value for how far the two cities are from one another. So using the distance between the two cities and the angle in between, Eratosthenes figured out that, well, okay, he got something like, so the angle is about 1/50th of a full circle, so the distance between Syene and Alexandria should be about 1/50th of the Earth's circumference. And then he got an answer using just a simple calculation of, okay, well, if this distance is 1/50th of the circumference of the Earth, then what's the whole circumference of the Earth? And the answer that he got was somewhere around 40,000 kilometers, which is basically the right answer. You guys can look up the circumference of the Earth. He was almost spot on with his answer. It's obviously going to be a little bit off because the tools at his disposal were not as refined, I guess, as the tools of today. But he was able to calculate with the simple tools of, his eyes making the measurements of first making the observation of this peculiarity with the shadows, and then making a couple of measurements of the angles, and having somebody pace out the distance between the two cities, and he was able to calculate the size of the Earth as a result. So there's an example of the power of math. Now, we can extend this farther. There is more to the story than just mathematical patterns appearing in nature, like in plants and things like that. So what I've found, and maybe my view is a little bit biased from being a student of astrophysics, but in physics, what we tend to use for almost everything, basically everything, honestly, unless we're trying to talk about things in a simple manner just so that we can understand it better, when we're actually trying to write things down, descriptions of how the universe works, we always write it down in the language of math. And the thing is that if you look at the world around you and you look at things like plants and animals, and you see all this expression of biology happening around you, if you zoom in on biological processes and you look at what makes this process actually happen, if you zoom in with like a microscope and you watch a biological process play out, you'll see that it's governed by the rules of chemistry. When you start talking about atoms and molecules and bonding and metals and non-metals and all these words that you guys probably heard before, maybe from me and maybe from others. But you find that when you zoom in, you can start by talking about an organism, and you're in a biology class, and then you zoom in, and all of a sudden you're talking about atoms and molecules, and you're using the language of chemistry to describe these biological processes. But then the thing is, for chemistry, if you zoom in on those atoms and molecules, you'll find that they're governed by the laws of physics. And those laws of physics are written down in the language of mathematics. So if you think of it as biology requires a foundation in chemistry, which requires a foundation in physics, which requires a foundation in math, then you get that math is possibly this sort of fundamental structure of the universe. Now, we haven't confirmed that or anything. No, there's no consensus that for sure the universe is mathematical in nature, but it does appear to sort of be that way. And I found this neat pyramid explaining the sort of the difference, the different areas of study. And of course, they all study different things, so it's not like all of chemistry is contained in physics. I mean, in a sense, you might be able to say that that it is. A lot of people disagree with that, and I don't stand firmly on one side or the other because I haven't studied enough. But like, it's not like studying physics suddenly makes all of chemistry totally obvious to you, or that studying chemistry makes biology totally obvious to you. The different areas do focus on different things, but in this pyramid, it's basically saying that, you know, arts requires this foundational understanding of social sciences, and then if you poke around at what makes social science what it is, you get psychology out of it as a result. And then if you poke around psychology to figure out its sort of root foundation, you get biology. And then, as we just talked about a couple of minutes ago, from biology, if you poke around and zoom in, you get chemistry. And if you poke around and zoom in, you get physics. And if you poke around and zoom in, you get math. So it looks like, on this sort of grand scale, that the universe is mathematical. Now, so yeah, here, this is just, you don't really need to pay attention to this too much. I'm just explaining a little thing because this is what I study, is that there are different areas of all these subjects. So, you know, if you're looking at physics of the biggest things in the universe, you don't necessarily need to talk about biology in there. But there is an area of physics that's looking at the tiniest things that make up the world. So like sort of the most basic building blocks of everything that we see around us and how those things behave around each other. So what happens if two particles bump into each other, things like that. And to describe what those building blocks are and, you know, how heavy they are and how they behave around each other and all of that, we use math. So in a sense, we're using math to lay out the groundwork for the building blocks of everything that we see. And in a sense, you could see it as using math to try and describe the universe at its tiniest, most basic scale. So in that sense, this sort of reinforces the idea that math is at the root of a lot of things in the universe. And this is just to scare you, basically. Don't stress out. We're not going to study anything like this in our physics unit, but this is just to show you that our sort of understanding of how the tiniest things in the universe work are contained in equations that look like this. And that's the thing. They're equations. It's basically math explaining how the tiniest things in the universe, you know, what they are and how they behave. And this just don't worry about this at all. This is not anything that you need to worry about. Neither is this, but just to show you that we can describe things in the universe using the language of math, and that's how we're able to understand these things that go on around us. All, if you zoom in far enough, you'll end up hitting math at some point. So that's it. That's all I got for you for this lesson. I know this was a bit long. That was partly intentional because um, for this first week, I don't want us to get into. I don't want us to dive into a subject that's going to require a lot of thought and study right away. So I thought I'll start off with this introduction of math in nature and how we use it and why it seems to be important. Um, and hopefully this will take you, a class and a bit to get through, and then later on in the week, or perhaps next week, we can start talking about the metric system and dive into our geometry unit. So yeah, if you have any questions about anything that we've studied in this lesson, let me know. If you have any questions about how the class is going to be set up and things like that, let me know about those too. Um, I think that's about it for right now. I will be sure to give you guys updates when I hear about how assignments and tests and things like that will be running. But yeah, if you guys don't have any questions, then I will see you all in the next video. Have a good one.